In volume 1 we saw how we can find the area of a right-angled triangle. We then extended that concept to find the area of an isosceles triangle. In this video we're going to take the same idea, but we're going to extend it using trigonometry in order to allow us to find the area of any arbitrary triangle. But let's start out by refreshing our memory of how we calculated the area of an isosceles triangle back in volume 1. So I'm going to start out by drawing an isosceles triangle. So something a little bit like this. And we know that an isosceles triangle is called an isosceles triangle because it shares two of the angles as the same angle, and because of that, two of the edges have the same length. Now, due to this relationship between the angles and the lengths of two of the edges, we also know from volume 1 that if we dropped a line down from our top vertex down to the base such that it meets the base at a right angle, and we could think of this line as representing the height of our isosceles triangle, so I could label this h, we know due to the relationship of the angles and the edges that this line subdivides our base edge into two even halves. Therefore, if our base had a length of c, each half would be a length of c over 2. Now we can see that it's also divided our isosceles triangle into two separate right-angled triangles. The area of a right-angled triangle is very easy to calculate. It's simply half times the length of the base times the height, which means the area of each of these triangles is a half times c over 2 times h. But of course, the area of our entire isosceles triangle is equal to the area of this triangle plus the area of our other triangle. In other words, it's equal to 2 times the area of any one triangle, because these two triangles are identical. We have two of them. The 2 and the half cancel, and that means that the area of an isosceles triangle is equal to c over 2 times h, which can also be written as a half ch. So that's the area of an isosceles triangle, but how can we extend this to work for a generic triangle, any arbitrary triangle? Well, allow me to draw some arbitrary triangle. Now, do note that the workings that we're going to do and the equation that we come out with works for any triangle, absolutely any triangle, but of course, to demonstrate this, I need a specific triangle, and the triangle I'm going to draw is going to look something like this. But of course, these workings really do work for any triangle. So we have some arbitrary triangle. Now, when we were working out the area of the isosceles triangle, we achieved that by dividing it into two right-angled triangles, because we know how to calculate the area of a right-angled triangle. Well, we can do the exact same thing with our arbitrary triangle. If we were to divide this into two right-angled triangles, so we drop an edge down from one of the vertices to an opposite edge, such that it meets that edge at a right angle. In doing so, we've created two right-angled triangles, and we know that if we can calculate the area of each of these right-angled triangles and add them together, we get the area of the isosceles triangle. Now again, we could label the length of this edge as h, because we know this kind of represents the height of our triangle. And if we knew that the total length of our base edge, so the total length of our original base edge, if that was a, then we could call one half of the base edge a1 and the other half of the base edge a2. That is to say, a1 is the length of this part of the edge and a2 is the length of the remainder. And we of course can see quite clearly that a1 plus a2 is equal to a, because we've split a, therefore the two parts that made up a, if you add them together, you're going to get the total length of a. But unlike an isosceles triangle, we have no guarantee that these two parts are the same length, because it's only an isosceles triangle with the relationship of the angles and the edges that if we were to divide it in such a way, it divides it nice and uniformly into two even halves. It's only the isosceles triangle, or an equilateral triangle in fact, that would work in that way. An arbitrary triangle, you have no such guarantee, so we cannot make any assumptions about a1 and a2. However, we can still work out the area of each right-angled triangle. The area of this right-angled triangle over here on the left-hand side is going to be equal to a half times our base, well our base is A1, times our height. The area of this right-angled triangle over here on the right-hand side is going to be equal to 1/2 times the base, in this case is A2, and again times the height. Therefore, the area of our entire arbitrary triangle is equal to the area of this triangle plus the area of our other triangle, which means it's equal to 1/2 times A1 times height plus 1/2 times A2 times height. Now, if we took this area equation, which I guess we should know that this is, of course, the area. If we took this area equation, we could factorize that based on a common factor. We've got something plus something else. We could factorize this. We've seen factorizing in volume 1. And the common factor in this case is 1/2 times h. We have 1/2 times h in both of the parts of our addition. So therefore, we could say that a is equal to 1/2 times h times A1 plus A2. If we expanded this out, we get 1/2 times h times A1 plus 1/2 times h times A2. We get the exact same equation as we had here. But notice A1 plus A2. We've seen that A1 plus A2 is equal to A. It's equal to our entire length of the base. So our area is equal to 1/2 h A. 1/2 times h times A. Now, we could, in a triangle, if we knew the length of one of the edges, we could say, well, that edge is A, so we could know the length of A, but we don't know the length of H. This is something that we have constructed within the triangle, and we don't yet know the length of it. So how do we find the length of H? Well, this is where trigonometry comes in. We have a right-angled triangle here. So if we want to find this edge, we're going to need to know one of the angles in the triangle, and we're going to need to know one of the edges in the triangle. Well, notice, we either need to find this angle or this angle down here. Well, the angle up here at the top isn't the full angle. If we knew the full angle of the triangle, that's not the angle we're dealing with because we've suddenly split it using this new edge. So this angle is of no use to us. So we need to know this angle down here. We'll call that angle theta. Moving on, we need to know one of the other edges in the triangle. Well, this edge down here is A1. It's not a full edge in the original triangle. We're not going to know the length of it. So again, this is of no use to us for finding the length of H. We need to know this edge of the triangle, which I'm going to refer to as B. And we can see that this edge of the triangle is of absolutely no use to us in this case because our right-angled triangle here is relating to this angle, and one of the edges in this right-angled triangle, it doesn't relate. In this case, because we're dealing with this triangle, it doesn't relate to this edge. So we've got an edge that we know, B, and we've got an angle that we know, theta. So if we know theta and we know B, we can represent these edges in terms of their relationship to theta, find the trigonometric ratio that relates these edges together, and therefore we can find the length of H. So if this is theta, well, in our right-angled triangle, we know that B must be our hypotenuse and that H is opposite our angle. So we're dealing with the hypotenuse and the opposite. That means we're dealing with sine. So sine of our angle theta is equal to the opposite over the hypotenuse. Our opposite is H, in this case, lowercase h, and the hypotenuse is our B. So the sine of theta is equal to H over B. That means that B, my apologies, we're trying to find H, not B. That means that H is equal to the sine of theta multiplied by B, which is more commonly written as B sine theta. So we now have that H is equal to B sine theta. Well, if the area is equal to half HA, that means our area is equal to 1/2 times B sine theta times A, which this is more commonly written as the area is equal to 1/2 AB sine theta. This is the area equation for an arbitrary triangle. But what does it mean? What do we have to be careful of here? Well, all we need is the length of two edges in our arbitrary triangle, in this case A and B. These can be any two edges in the triangle, so as long as you know any of the two edges. The thing you need to be careful of is that we must know theta is the angle between those two edges. So if we had a triangle that looks something like this, if we knew this to be A and this to be B, theta must be this angle here. We cannot use either of the other two angles, and that's because the way we have derived this equation, it assumes that theta is between our edge A and our edge B. So that's really, really important. But as long as you remember that, if you have two edges in the triangle and the angle between those two sides, we can now find the area of that triangle. So let's put this new formula to the test. I'd like you to answer just a few questions that use this formula. So I'm going to bring up a new whiteboard for that. So we hide all these guys out, bring up a new layer. Fantastic. Scroll right back up. And I'm going to start out. So question 1. I'd like you to find the area of the following triangle. So I'm going to draw a triangle. I don't know, something like this. I'm going to give you some of the pieces of information of this triangle. I'm going to tell you this angle is 50 degrees, this edge is 7 units long, and this edge is 4 units long. So with that information, you can calculate the area of this triangle. So go ahead and pause the video, give this an attempt. Once you have a solution, or if you get stuck, unpause the video and I will work through the solution on the whiteboard. Okay, welcome back everyone. So we know our equation for an arbitrary triangle, for the area of an arbitrary triangle, is the area is equal to a half AB sine of theta. Again, the important part here is that theta is the angle between A and B. So we could say that A is 7, B is 4, or the other way around, it really doesn't matter. But what's important is that our angle theta is this angle between those two edges. So our area is equal to a half times, let's say A is 4 in this case, times B, let's say, is 7, times the sine of our angle is 50 degrees. So if we then used a calculator for this, so bring up a calculator, we're going to take 0.5, so 0.5 is a half, times 4, times 7, I know that's going to be 14, and then we can multiply that by the sine of 50. Well, I am in degrees, so 50, the sine of 50 is 0.766. If we click equals, it tells us that the area of this triangle is approximately equal to 10.725. So our area is approximately equal to 10.725. Fantastic. So I do want to set just one last question to test your knowledge of this equation right here. So question 2. And again, I'd like you to find the area of the following triangle. So here's a triangle. Fantastic. And we do know some of the information of this triangle. We know that this edge is 5 units long. We know this edge is 6 units long. This angle is 55 degrees, and this angle is 82 degrees. To find the area of this triangle for me, when we come back, I will work through the answer on the whiteboard. Okay, welcome back everyone. So our area equation again is the area is equal to a half AB sine theta. Now what have I been stressing as the important part to remember about this equation? The important part to remember is theta must be the angle between the two edges that we choose to use. We only know these two edges, and that means we must use this angle as theta. The 55 degrees in this case has no bearing on our result. We can simply ignore it. However, we must take the 82 degrees to be our angle theta, and our edges of 5 and 6 units length to be A and B. It doesn't matter which order we take them in, but they need to be our edges A and B. So this means our area is equal to a half times 5 times 6 times the sine of 82 degrees. Well, a half times 5 times 6 is a half of 30, which is 15, times the sine of 82 degrees, which means if we use a calculator to work this out, we take 15, multiply it by the sine of 82, which is 0.99, and that tells us that the area of this triangle is approximately 14.854. So our area is approximately 14.854. 5, 4. Okay, so to recap, we saw how by creating two right-angled triangles from our generic triangle, we can find the area of that triangle. Again, we did this as I jump back to our earlier whiteboard. So let's hide out these, bring back these. There we go. Make sure we bring back everyone. There we go. So we saw we did that by constructing a line from one of the vertices down to the opposite edge, such that it meets that edge to divide it at a right angle here. So we do have two right angles. That creates two right-angled triangles. We added the area of those triangles together and saw that that actually gives us the equation A is equal to a half times H times A. And then we saw how we can use trigonometry to find the length of H given our angle theta and edge B. So again, this gave us the equation for the area of our triangle as A is equal to a half AB sine theta. And again, the only important thing to remember is that A and B can be any two edges in that triangle as long as theta is the angle between those two edges. So that is going to conclude this video. Thanks a lot for watching, everyone.